Biostat 66111, skills for the rest of your life, bootstraps and probability, it's the bread and butter, baby, what's your jam?
Greetings, Bio 6611. In this lecture, we're going to discuss model selection approaches, or ways of identifying the optimal or best model for a given data set and the information we have. We'll start with a little background and review of some different study designs, discuss a variety of methods, some of which will be familiar to us for model selection approaches, and show an example with what we call an all possible subsets approach. So let's start with a little background information. Depending on our study design and purpose of the study we've done and the data we have various considerations for how we might want to approach model selection and different things we might be concerned with. For example, if we have an epidemiologic study design or something of an observational nature, we may have only one or a few exposure variables of interest, and there may be interactions that we know or want to explore. We also know, since it's observational, we may wish to adjust for potential confounding factors that may be present between groups, since we have not randomized them. Also, we may potentially be collecting a large number of variables and a lot of information without necessarily a meaningful scientific or historic reason to collect that information. This can then help us, though, in this process, identify important predictors and/or potential confounders via model selection processes. In the case of doing a clinical study design, for example with a randomized study, we generally have some intervention effect that's a variable of primary interest. Because of that randomization, little or no confounding is expected, although we may have some possible stratification built into the study design. For example, if we want to ensure that there's equal or approximately equal proportions, let's say, of males and females between two randomized groups. In the model that we're fitting, we'd adjust for variables that we used for stratification or potentially matching to increase our precision. And in general, these variables would be identified during the design phase of the trial before we actually implement the study and enroll participants. Model selection is not always necessary or desired for clinical study designs because we generally try to predefine the models a priori based on existing evidence and information. That's not to say we might have some variation or evolution of the model after we see some of the information, but best practices would say we at least predefine the starting point we're going from. Finally, a third type of modeling that we haven't discussed too much this semester, but we will have in future classes, is the idea of predictive modeling. In other words, this could be from an observational or randomized study, but we wish to choose a model that best predicts an outcome for a future observation. Model selection is possible in this case, but may or may not be necessary depending on our intent. In general, though, a best practice would be to have some holdout sample, for example, a training and a testing set of the data, or some external data set for validation if we're interested in prediction, because we want to avoid the case where we build a model on our specific data set, but perhaps it doesn't perform as well in a future set of data that we collect due to either overfitting or being very specific to the one data set at hand. So moving from this consideration of study designs, we can discuss a few of the general considerations for model selection. And these will vary depending again on the type of models we're fitting in the studies that we've conducted. But in general, we want to ask ourselves, what was the goal of the modeling? Was it for some sort of estimation, to test a hypothesis test, or maybe to predict some outcome? We also want to consider the issue of type 1 error inflation, adequate power if we have that or not, and the potential for confounding and other issues. In our class specifically, we focused here on linear models, but we also should generally consider the form of the model. For example, next semester you'll learn about generalized linear and nonlinear models. We also know that there's transformations to make a variable fit the model assumptions, such as linearity in our case for linear regression, and in cases like this we can think of the log transformation or maybe a square root. One other overarching consideration is our desire for a parsimonious model that again tries to avoid that issue of overfitting. We don't want to fit a model that perfectly predicts or describes our dataset because it's unlikely to be generalizable to the future and probably contains too much information. Some of the things that we will see in the following slides is that models can be compared in a variety of different ways. For one, we have numerical differences, so there's not necessarily a statistical difference that we're evaluating. Although in other cases, things that we've seen before like the partial f-test, we do have statistically significant differences that we evaluate. And finally, we have this third category of scientifically meaningful differences, where it's possible we can look at two different models and identify one as better or suboptimal depending on the context at hand and the variables we may have to include. So let's discuss some methods for model selection. Again, some of these will be familiar to us from previous lectures. For example, one of the tools we can use is either the coefficient of determination r squared, or more realistically, the adjusted r squared value. Because we know that no matter how strong or weak an additional variable is, based on the breakdown we've done of our sum of squares, the sum of squares for the model will never decrease as long as we add a new variable. If the new variable is actually a meaningful or strong predictor, we'll see that that sums of square explained by the model will significantly increase. Whereas if the variable is a poor predictor, it will either change very little or potentially stay the same if there is no predictive utility. This implies then, though, that our r squared that's not adjusted, that we calculate as the ratio of the sums of square of our model divided by the total sums of square, will also never decrease with the addition of new variables. This means that we might think that the larger the model, the better the fit. To account for this, though, we've introduced previously this idea of the adjusted r squared. Here we see that we adjust for the sample size and the number of predictors as part of the relationship with that r squared term. In this case, p is the number of variables we have in our model, excluding that intercept term, and we can show that it could increase or decrease when a new variable is added with this correction. In general, a larger value is desired, however, no single benchmark exists for how much of an increase is considered meaningful. Another tool we already have in our toolbox is the f-test or the partial f-test. We know that the overall f-test is meaningful to test the question of, are any variables in my model useful at predicting or being associated with the outcome? We also know that then the partial f-test will compare nested models based on some overarching full model of interest. We can see if some model with fewer predictors or a subset of those is meaningful. If we wish, though, to compare non-nested models, we can't use these approaches. For example, we can't directly compare a model with age and height to a model with age and weight as predictors. Instead, we would first need to fit a model with age, height, and weight, and then evaluate if the reduction by removing weight or height is meaningful. That's one potential limitation to these tools that we've already learned, but still are useful to evaluate the question, especially with respect to nested models. A new set of tools that we haven't discussed previously is the family of model selection criterion. And we're going to discuss a handful of them, noting that there are many, many more classes that exist beyond the AIC and the BIC that we'll discuss. But starting off here, we have the AICc information criterion, or AIC. It's a calculation based on the goodness of fit and includes a penalty for increasing the number of parameters in the model. So we see here that AIC is this pretty simple looking formula calculation there, where k is the number of parameters in the model. And then the natural log of L, our likelihood here, is the log likelihood for our model. Specifically, things that you'll discuss more in statistical theory in next semester, L is the maximized likelihood function for the model. For AIC, we can note that the models do not need to be nested, although they potentially could be. We could use this in place of the f-test and the partial f-test on the previous slide. The best model will have the lowest AIC out of all models that we're considering, and there is an arbitrary rule of thumb that a difference of 2 is significant or meaningful. This would be a case here, though, where we're looking at a numerical difference and not a statistically significant difference because we don't have some formal statistical test with these model selection criterion. We're just summarizing the information included in the model in the k number of predictors or parameters in the model with respect to the overall likelihood based on the data we're providing to fit the model. Like r squared and our adjusted r squared, though, there is some criticism that the AIC may be favoring models with more parameters based on the standard definition on the previous slide. In other words, it still may be too optimistic to favor larger models with more predictors. This can be especially true if we happen to have a smaller sample size, and it could lead to that issue of overfitting, where we're not appropriately describing and being able to generalize the information from our model to either future data sets or problems. Fortunately, various versions have been proposed to try to account for this presumed over-optimism. For example, a corrected version was calculated by taking our AIC value plus then this just extra penalty term here, where we take 2 times the number of variables in that specific model squared plus 2 times the number of variables divided by the sample size minus the number of variables minus 1. And we would then similarly interpret, like we saw in the previous slide, the model selection criterion for the corrected AICc information criterion, where the smallest value is considered best, and a difference of 2 would be considered a significant or meaningful difference as a rule of thumb. A second family of these information criterion is known as the BIC, or the Bayesian Information Criterion, also known sometimes as the Schwartz Information Criterion, or SIC. It's similar to the AIC in that it is based on the goodness of fit and includes a penalty for increasing the number of parameters in the model. So we see here we have our penalty based on the sample size and the number of parameters, but it's a slight twist from what we saw previously for the AIC. Like the AIC as well, we don't need to have nested models to compare between them. We also can identify the quote-unquote best model with the lowest BIC. There has been a little more work to propose some of these changes that might be meaningful or to evaluate the differences with BIC by Cass and Rafferty. And what we see here is that we have a summary where the change of BIC between 0 and 2 is considered minimal. So in other words, whatever model has the higher BIC, there's not really a significant difference between them. And so if that larger BIC value, so it's not the smallest, has maybe fewer predictors, it might be worth choosing that model over the absolute lowest or minimum BIC model because of the fact we're trying to achieve, again, that parsimonious model. However, as the difference between the models grows, we see that we get more and more evidence suggesting that the model with a lower BIC may be favored. Another criterion that we can use is known as Mallows Cp. This can be used to compare 2 models in a nested sense with a full reference model that we're comparing to. The calculation we see here on the screen is a ratio of the sums of square due to error in our reduced model divided by the mean square error estimated by the full model. Then we subtract some terms to penalize for the sample size and the number of predictors in the reduced model. Mallows Cp is attempting to balance the statistical trade-off we have between the bias and the variance, or the bias-variance trade-off, because we would like an estimate that's as minimal bias as possible, but usually this comes at the expense of increasing the variability we may have. So if we can try to find a compromise between those two for a generally less or unbiased estimate with low variance, that's considered optimal. However, the approach of Mallows Cp has a few assumptions or considerations that may be fairly strong. The full model, for example, is assumed to be unbiased and includes all relevant predictors. That means we haven't forgotten any of the relevant predictors either that are in our data set or that we didn't know to collect. Also, that assumption of being unbiased may be a strong assumption as well. The subset models then with smaller values of Cp would have a smaller estimated total variation in their predictive responses. So we would be looking at a smaller Cp as again, better model fit. We can note then again that Cp is penalizing the addition of variables to the model to try to help prevent overfitting and identify those parsimonious models. Some extra considerations though and unique connections to some of the previous topics we've discussed. When comparing 2 models that have the same value for a given number of predictors p, the model with the lower Cp is considered the better model between the two. Mallows Cp can be used then to determine how many variables are in the best model, since it will achieve a value of approximately p plus 1 if the mean square error of our reduced model is roughly equal to the mean square error for the full model. If important predictors are omitted from the full model though, we'll see that the estimate of Cp will be greater than p plus 1. When Cp is near p plus 1 though, the bias is assumed to be small. Versus if it's much greater than p plus 1, there will be substantial bias, and we can note that important predictors may have been omitted from that model with respect to whatever our full specified model was. A few interesting connections can be made where for linear regression specifically, the standard AIC and the Mallows Cp are technically equivalent in what they would identify as the optimal model with respect to a minimum value for either AIC or Cp. And we can also note that Cp is related to the partial F statistic based on this relationship between the number of predictors in the reduced model and those we removed from the full model, P and K respectively. So with these criteria reviewed, we can introduce one approach to how we identify what truly might be the best model given the information we have, and then illustrate this with an example. One way to do this is what we call all possible subsets regression. So in this case, we're going to assume we've identified the potential variables to include in our model. If we have questions about which variables to include, and for example, if we have that large observational study where we've collected a lot of data that may be extraneous, we'll discuss that a little bit more in a subsequent lecture. But once we've identified the subset of variables we're interested in, one of the ways we can identify the best model is through an all possible subsets regression. And this will fit all possible subsets of variables from the model. The most promising models then can be selected based on any of the previously discussed measures we talked about, including R-squared, any of the model selection criterion, Mallows Cp, or even directly looking at things like the mean square error. There are a few considerations to keep in mind here, and the fact that there is, again, like in much of statistics, no free lunch. The different measures, depending on what you choose, can arrive at different best or optimal models. In other words, they aren't all equivalent, even though we did notice some of the relationships between things like AIC, Mallows Cp, and the partial F test for linear regression. A second consideration is that all possible subsets regression can quickly become computationally prohibitive. With p total variables of interest that we might have, there are a total of 2 to the p possible models. So we can imagine if we had 20 predictors, 2 to the 20th power is quite the number of models that we would have to fit and identify all of these different criterion for. Fortunately, with respect to this concern, there are various approaches that exist to try to get around this or approximate an exploration of the model space, such as simulated annealing and other approaches. A third consideration then is that if you were looking at a hierarchical model, for example, you suspected you need an interaction term or potentially need some sort of polynomial terms in your model, some of those subsets will, by its definition of looking at all possible subsets, exclude either the main effect terms for the interaction or the lower order polynomials, and therefore they may not make sense for a given model. In those cases, we have to look through the results and exclude or ignore those models where we're getting rid of the hierarchical nature of the model we've proposed. So let's look at an example that we're familiar with, the FEV dataset, to identify the best model here. And we only have a handful of predictors at our disposal for age, height, sex, and smoking status. For simplicity in our problem, we will assume there are no interactions to be concerned with, no need for polynomials, or anything else like that. Just a simple model with these 4 terms. Given that we have 4 predictors, we can note that in all there's a total of 16 possible models we could fit. And again, it's important to note here at this stage, if we had some predefined reason for including all 4 predictors in the model, we could jump right ahead to fitting that full model with the 4 predictors and not necessarily even identifying the subsets of these models, because we have some maybe scientific or clinical reasoning for including all of these predictors in the model itself. But here again, let's assume that we just want to identify, based on the data we've collected in the FEV dataset and these 4 predictors, what might best be the combination to model FEV or predict FEV. We'll introduce very briefly some R and SAS code we can use and then look at the results in R. We see at the top here we are just reading in the data from our CSV file into R and also defining some indicator variables as 1 and 0 with our little as.numeric function here for the purpose of just more nicely presenting the results in the following slides. To implement this all subset regression, there's of course a variety of different packages and functions we can use. One of which, though, for linear regression comes from the LEAPS library and is the reg subsets model, or function. Here we see we're fitting the model where FEV is our outcome and we have age, height, sex, and smoking status as our predictors. There's a couple different methods that we can implement with this all subsets regression with the reg subsets approach, and so we'll specify method equals exhaustive. And in this case, we want to see just all 16 models, so we'll just say we want the 8 best models for each number of variables. So if there's only 1 predictor, 2 predictors, 3 predictors, or all 4 predictors. One of the things about this function, though, is that there isn't necessarily a nice summary table to get the information out of, so we have to create here an object to summarize our results by extracting things like our R squared, adjusted R squared, the Bayesian information criterion, and Mallows Cp from the object output. In the case of SAS, if you're using that, we can see here that presuming we've already read in the data, we can specify some of these indicator variables of interest, and then we simply add this selection statement and specify the different criteria we wish to have spit out or feed back to us to evaluate for potential significance in comparing the different models. So let's take a look here, though, at the version in R from our LEAPS package. We can break down the output that we've created here, and that the first chunk of columns represents indicators for if a given variable is included in the model. What we can see is that the intercept is included in each of our models, and it has not fit the model with no predictors at all. So if we were interested in that, we might have to fit that additionally as another term. We can see, though, that by looking at each one of our rows, we see that we have a collection of variables here with 1 predictor, 2 predictors, combinations with 3 predictors, or that one full regression model with 4. Now, if we break down briefly each one of our columns of output, we can identify what the optimal model might be. And in this case, we see that R squared and the adjusted R squared actually agree in our given context, where we see that the model with 4 or this model with 3 have both the largest values for the adjusted R squared or the R squared at about 77.5 or 0.4%. We can see here that if we want to go for then that more parsimonious model, we would choose this model with 3 predictors, and we can see that the only thing not included is smoking status. If we were looking at BIC or Mallows Cp, remember, instead of the largest value, we want to look at the smallest possible value. Here we see that that is negative 948.480, and if we compare that just to our previous with the adjusted R squared and R squared that was identified, we do see it's a difference of about 4 points. And so based on that criterion from Cass and Raftery, we might identify that there does appear to be some evidence that the simpler, more parsimonious model with 3 predictors might be optimal. Finally, we can look at Mallows Cp, where we see that, again, this is just based on the definition of it, but our full model with all predictors achieves that unbiased quote-unquote estimate of 5.000. Again, that's because we're assuming that the full model is unbiased and has all information we possibly need. We can then compare the Mallows Cp for all of our other models here to identify what one might be close to or similar to that value. Here again, we actually see a pretty similar story emerging, where the Cp for that same model that has age, height, and sex as our predictors achieves a pretty close value to 5, suggesting that it seems to be fairly unbiased still, even if we remove smoking status from this assumed full model. We can also note here that if we exclude things like age and height, those may have a much more deleterious effect on the optimal model, with the Cp values growing greatly into the thousands, suggesting again, with respect to that full model, we probably do have some bias that we are not accounting for. So we see here in this case, though, that using these different approaches generally arrives here at the same answer for what the optimal model might be. And what we could do at this point is actually fit it with GLM or LM or proc-reg and actually look at the beta coefficients and do some interpretations or hypothesis tests or predictions depending on what our purpose was. A few closing thoughts here about model selection. Model selection is ultimately an art. There is no single best method to arrive at what we might consider an optimal model. However, we can note there are several wrong models or approaches due to issues such as high collinearity between variables, or if we have models that we lose their hierarchical status, because that again leads to estimates that don't necessarily do what we want. One thing to keep in mind is that our model selection should be first and foremost driven by knowledge of the subject area and by our hypotheses. This is one of the cases where it's really optimal to work with great collaborators who take the time to explain their problem and the data they're working with so you can fit or identify the most appropriate or best model. We didn't quite see this here, but in general, different strategies could lead to different sets of variables being included in the final model that you use for inference. Again, it doesn't mean one approach is more right or wrong than another. They just have different trade-offs built into the different approaches we're looking at. A good analysis in general should point out, though, that there are different possible models and that there may be more than one adequate model detected in any given analysis. And in the next lecture about variable selection, we'll note one way to address this with an idea known as model averaging. And just as a final closing note, for prediction modeling, we should utilize either an external validation set or do some sort of training and testing subset or use cross-validation approaches to identify the most appropriate model. And so that will close the general idea and approach of model selection before discussing some considerations for selecting variables for your model.